if we had these two objects at the positions they're currently at, balanced on a light meter stick or something, a light support balanced at a certain point, then depending on where this point is, the system might tend to tip the balance this way or this way. If this fulcrum was over here, then any mass here subject to gravity would tend to rotate it in the clockwise, would tend to rotate the system in the clockwise direction. Okay, if we just had this mass in a fulcrum here, and let's assume we have no significant mass of the supporting entity, whatever this is, a meter stick or whatever, assuming this mass is a lot larger than that of the meter stick, so that the mass of the meter stick is negligible. If we balance the thing anywhere to the left of this mass is going to tend to make the system rotate like this. And the same with this. If the fulcrum is anywhere to the left of this object, especially if it's like over here, that's going to tend to make the system rotate this way. Okay, so if the fulcrum was here instead of here, the system would clearly rotate in this direction. And as we talked about in class, the vector that represents that direction of rotation is given by the right-hand rule. You turn your fingers in the direction of rotation, and your thumb, which you probably can't see because of the board, but your thumb is going to point this way. That's the direction of the rotation vector. Now you want to get used to that, and we mentioned that in class. We talked about it in class, okay? So, if the fulcrum was here, this would give you a rotational tendency into the board. Okay, right-hand rule, thumb goes into the board. Similarly, if the fulcrum is over here, then the rotational tendency from this one and from this one would both be, well, both would tend to rotate the thing in this direction, so that the vector direction of your rotation would be, your rotational tendency would be here out of the board. But both of these would have the same tendency, so the system would rotate in this direction. Now, that tells us that you can't put the fulcrum to the left of this one, and you can't put the fulcrum to the right of this one, something you know from having picked up unbalanced objects. Okay, you know you have to grab this thing somewhere in the middle, and you also know you got to grab it closer to the bigger mass than you do to the smaller mass. Okay? So, how is it that the rotational tendencies could balance? Turns out they balance if the rotational tendency from this mass that has a vector into the board, that's represented by a vector into the board, if that rotational tendency is equal and opposite to the rotational tendency of this mass about this axis. So, well, this rotational tendency to this mass would be out of the board. Okay, so this mass is tending to rotate the system one way, this one the other way. This would be clockwise, this would be counterclockwise. The position of the fulcrum for which the rotational tendencies would be equal and opposite, well, let's think about how the distance from the fulcrum to the mass affects its rotational tendency. The further the fulcrum is from the mass, the greater the rotational tendency of that mass about the fulcrum. Okay? So, if we move the fulcrum from, let's say, the position of this mass to the position of this mass, the rotational tendency of this mass will be increasing as we move this way. The rotational tendency of this mass will be decreasing. Now, the rotational tendencies are in opposite directions. There's some point in between where they would match. And if you think about it, the fact that the rotational tendency depends on the product of the distance from the fulcrum to the mass And on the mass, if this mass is twice as great as this mass, which it is, then you probably need to be half the distance from this mass that you are from this mass. Or that is, twice as much mass, you got to be twice as close to it. Now, where's the point that's twice as close to this mass? It's 2/3 of the way between this mass and this one. Okay, so there's a center of mass here. Now, I call this frame the center of mass frame. Okay, if the fulcrum is positioned so that the center of mass right now is at that fulcrum, then what's going to happen? Remember that this one needs to be twice as close to the fulcrum as this one does. Well, this one's moving toward the fulcrum twice as fast as this one is. So this one's going to move twice as far in any time interval as this one does. And that's, you're going to have to think about it just a little bit, but that assures that you're always going to be, that this one's always going to be twice as close to the fulcrum as this one. Okay? So the center of mass here remains the same. It doesn't matter where these are. The center of mass is going to be where it is, and if you're in the center of mass frame for two objects, the total momentum is going to be 0. Okay, that's a characteristic of the center of mass frame. In that frame, momentum before and after collision is 0. If kinetic energy is to be conserved, along with momentum, it's going to turn out, and not that difficult to work out, that the velocities are going to have to reverse. The velocity of this one before collision is going to be at the same as its, well, it's going to be equal and opposite to its velocity after collision. It's moving 4 meters per second here. After collision, it's moving at 4 meters per second in this direction. This one's moving at 2 meters per second in this direction. After collision, it'll be moving at 2 meters per second in this direction. Okay, so in the center of mass frame, the velocities just reverse. The two objects don't exchange velocities. The velocity of each, the speed of each object stays the same, but its direction of motion changes. It reverses its direction of motion. Okay, that's a characteristic of the center of mass frame. We haven't yet talked about how to calculate the center of mass frame. It's quite easy, but that's why it's significant. In any other frame, of course, the center of mass of this frame is going to be moving. Now, how fast is the center mass of this frame moving in our new coordinate system, where the velocity of that coordinate system is, respect to the old one, is 3 meters per second. So let's say this is a new coordinate system. I keep wanting to put the word coordinate in there because we can talk about the system consisting of the two objects, or the system, the coordinate system from which we're measuring the velocities of those two objects, velocities, positions, whatever. Okay? Okay, so in the new coordinate system, the center of mass here is moving at -3 meters per second. So the center of mass moves in this coordinate system at -3 meters per second. So the momentum of the whole system here I'll say the momentum of the entire system is total mass times velocity. Total mass being 0.3 kilograms. The velocity being -3 meters per second. What's that equal to? 0.3 kilograms times negative 3 meters per second. Is that equal to something else you see on the board? Well, yeah, it's equal to this. So the total momentum in this system is the same as the momentum of the center of mass applied to the mass of the whole system. And that's kind of a pretty neat idea. So something that you really probably ought to try to lock in and think about. It can be very helpful in solving some of the problems you're going to see in just understanding the whole concept of momentum.